On a clear night, as you gaze up at the constellation Leo, there's something extraordinary hiding among those distant points of light. Something that might change everything we thought we knew about life in the universe. Just 124 light-years away, a world unlike anything in our solar system is quietly orbiting a red dwarf star. And what we've discovered there has sent shockwaves through the scientific community. Welcome back to another cosmic journey, where we explore the mysteries that keep astronomers awake at night. Before we dive into what might be the most significant discovery in human history, I'd love to know where you're tuning in from tonight and what time it is in your corner of our small blue planet. And if you find yourself drawn to these explorations of the unknown, I'd be ever so grateful if you gave this video a like and perhaps subscribe to join our growing community of cosmic wanderers. Let's get started. The story begins now. Tonight, we're venturing into territory where cutting-edge science meets the profound question that has haunted humanity for millennia. Are we alone? The answer might be hidden in the atmosphere of a world called K218b. And what the James Webb Space Telescope has found there is nothing short of revolutionary. This isn't just another exoplanet discovery. This is a world that challenges every assumption we've made about where life can exist. A planet that exists in a category so new, we've had to invent entirely fresh terminology to describe it. And the molecules floating in its atmosphere, they've got scientists around the world either celebrating or frantically double-checking their calculations. But here's what makes this discovery truly extraordinary. The James Webb Space Telescope didn't just detect water vapor or methane or carbon dioxide, though it found all of those too. No, what has everyone's attention is something far more provocative. A molecule that, as far as we know on Earth, can only be produced by living organisms. A chemical signature that might represent our first genuine glimpse of life beyond our solar system. The story begins in 2015, when the Kepler Space Telescope first spotted this enigmatic world during its systematic hunt for planets orbiting distant stars. But like many groundbreaking discoveries, what seemed like a routine detection would eventually reveal itself to be something far more profound. K218b wasn't just another planet. It was a key that might unlock one of the universe's greatest mysteries. Picture a world unlike anything in our cosmic neighborhood. 218b is what astronomers call a sub-Neptune, a type of planet that sits right in that sweet spot between rocky worlds. Like Earth and gas giants like Neptune, it's about 2.5 times the radius of our planet and weighs in at nearly 9 times Earth's mass. But size isn't what makes this world special. It's where it lives. K218b orbits its star in what we call the Goldilocks zone. Not too hot, not too cold, but just right for liquid water to exist. The planet completes one orbit around its red dwarf host star in just 33 days, meaning a year on K218b lasts about as long as a month on Earth. Despite this close proximity, the cool nature of red dwarf stars means the planet receives roughly the same amount of light and heat that Earth gets from our Sun. But here's where things get interesting. This isn't a rocky world like Earth or Mars. Instead, K218b belongs to an entirely new category of potentially habitable planets that scientists have dubbed Hycean worlds. The name itself tells the story. A combination of hydrogen and ocean. These are planets with thick hydrogen atmospheres sitting atop vast liquid water oceans. Now, traditionally, astronomers thought planets with hydrogen-dominated atmospheres would be too hot to support life. The greenhouse effect from all that hydrogen should create surface conditions more like Venus than Earth. But recent modelling has revealed something remarkable. Under the right conditions, these hydrogen blankets might actually create a kind of cosmic thermostat, maintaining temperatures that could allow liquid oceans to exist beneath them. Imagine a world where the sky's thick with hydrogen, but beneath that alien atmosphere lies an ocean that could dwarf all of Earth's seas combined. A planet where the atmospheric pressure might be dozens of times greater than what we experience, yet where liquid water could flow and potentially harbour life forms we've never imagined. This is the world that the James Webb Space Telescope has been studying with unprecedented precision, and what it's found there has astronomers questioning everything they thought they knew about the requirements for life in the universe. When James Webb turned its infrared eyes toward K218b, it wasn't looking at the planet directly. Instead, it employed a technique called transmission spectroscopy, essentially using the planet's host star as a cosmic backlight. As K218b passed in front of its star during what astronomers call a transit, some of the starlight filtered through the planet's atmosphere before reaching our telescopes. Different molecules in that atmosphere absorbed specific wavelengths of light, creating a kind of chemical fingerprint that revealed the atmospheric composition. It's like looking at the colours of a rainbow and being able to tell what elements created each hue. But instead of a rainbow, scientists were analysing the invisible infrared spectrum, hunting for the molecular signatures that could tell us whether this distant world might harbour life. What they found was remarkable. The atmosphere of K218b is dominated by hydrogen, as expected for a sub-Neptune. But mixed in with that hydrogen are other molecules that paint a picture of a world that might be more Earth-like than anyone dared hope. Water vapour, though present in smaller concentrations than initially expected. Carbon dioxide and methane, both at levels around 1% of the atmosphere. And notably absent was ammonia, whose scarcity actually supports the hypothesis that liquid water oceans might exist beneath the hydrogen atmosphere. This chemical cocktail is exactly what theoretical models predict for a Hycean world. The presence of methane and carbon dioxide, combined with the shortage of ammonia, suggests that we might be looking at a planet where atmospheric chemistry is being driven by interactions between that thick hydrogen atmosphere and an underlying ocean. But here's where the story takes a turn that has the entire astronomical community holding its breath. Hidden in the spectroscopic data at the very edge of detectability is a signal that could change everything, a molecular signature that, if confirmed, would represent the strongest evidence yet for life beyond our solar system. The molecule in question is dimethyl sulfide, or DMS. On Earth, this compound has a very specific origin story. It's produced almost exclusively by living organisms, particularly marine phytoplankton floating in our oceans. When you smell that distinctive ocean breeze during a walk along the beach, part of what you're detecting is DMS being released by microscopic life in the water. DMS is what scientists call a biosignature, a chemical that, as far as we know, can only be created by biological processes. It's not like oxygen, which can be produced by non-biological means. It's not like methane, which can bubble up from geological processes. Dimethyl sulfide, at least on Earth, is the exclusive calling card of life. The detection of DMS on K218b is still preliminary, existing at what scientists call the 3 sigma level of statistical significance. That means there's about a 0.3% chance that this signal is just cosmic noise, a false positive created by the limitations of our instruments, or the complexities of analysing light that has travelled 124 light-years through space. To reach the gold standard for scientific discovery, the detection would need to reach 5 sigma significance, reducing the probability of a false positive to less than 0.00006%. But even at 3 sigma, this detection represents something unprecedented in the search for extraterrestrial life. Never before have we found such a compelling biosignature candidate in the atmosphere of another world. Never before have we had a molecule this strongly associated with biological processes detected beyond our solar system. Dr. Niku Madhusudan from Cambridge University, who led the research team, has been careful to emphasize what they are and aren't claiming. "That's not what we're claiming," he told reporters when asked about the detection of life, but in the best-case scenario, it's the potential for life. This measured response reflects the careful nature of modern astronomy, where extraordinary claims require extraordinary evidence. The detection of DMS on K218b is extraordinary, but it's not yet definitive. And that's where things get complicated, because while DMS is primarily biological on Earth, we can't assume the same is true everywhere in the universe. Recent studies have shown that dimethyl sulfide can be produced through non-biological means. It's been detected in comets, those ancient frozen relics from the early solar system, where life as we know it cannot exist. Laboratory experiments have demonstrated that DMS can be synthesized under prebiotic conditions using chemical processes that don't require living organisms. This creates a profound challenge for scientists trying to interpret the K218b data. The concentrations of DMS detected in the planet's atmosphere are thousands of times higher than what we see on Earth. If life is producing this molecule on K218b, it's doing so at scales and concentrations that dwarf anything in our terrestrial experience. Alternatively, there might be unknown chemical processes occurring in the exotic environment of a Hycean world that can produce DMS through purely geological or atmospheric mechanisms. The combination of a hydrogen-rich atmosphere, potentially vast oceans, and the unique chemistry that might occur at their interface could create conditions unlike anything we see on Earth. The uncertainty surrounding the DMS detection has created a fascinating divide in the astronomical community. Some researchers are cautiously optimistic, viewing this as the most promising biosignature detection to date and calling for additional observations to confirm or refute the finding. Others are more skeptical, pointing to the marginal statistical significance and the possibility of non-biological explanations. This debate reflects a broader tension in astrobiology between the desire to find life and the need to maintain scientific rigor. The discovery of life beyond Earth would be the most significant finding in human history, fundamentally changing our understanding of our place in the universe. But that very significance means we must be absolutely certain before making such a claim. The James Webb Space Telescope represents humanity's most powerful tool for investigating questions like these. Its 6.5-meter mirror collects infrared light with unprecedented sensitivity, allowing astronomers to detect molecular signatures in exoplanet atmospheres that were completely beyond the reach of previous instruments. Unlike the Hubble Space Telescope, which observes primarily invisible light, James Webb was specifically designed to hunt for biosignatures in the infrared portion of the electromagnetic spectrum. This capability is crucial because many of the molecules associate dioxide, methane, and potentially with life, including water vapor, carbon DMS, have their strongest absorption features in infrared wavelengths. The telescope's ability to achieve precisions better than 1 part in 10,000 during transit observations represents a technological marvel that has revolutionized exoplanet science. When K218b passes in front of its host star, the tiny fraction of starlight that filters through the planet's atmosphere carries information about its chemical composition. James Webb can detect variations in this filtered light that are smaller than the fluctuations you'd see in a perfectly steady LED bulb. This extraordinary precision is what made the potential DMS detection possible in the first place. The signal is so subtle that it exists right at the edge of what even our most advanced instruments can measure. It's a testament to both the capabilities of James Webb and the dedication of the research teams who have spent months carefully analysing every photon of data. But precision alone isn't enough to confirm the presence of life on K218b. The detection needs to be repeatable, statistically significant, and accompanied by a theoretical framework that can explain how such high concentrations of DMS might be produced and maintained in the planet's atmosphere. This is where future observations become crucial. The research team has identified specific instruments and observation strategies that could elevate the DMS detection from its current 3 sigma status to the 5 sigma threshold required for scientific discovery. Additional observing time using James Webb's most sensitive spectrographs could provide the definitive answer about whether dimethyl sulfide truly exists in K218b's atmosphere. The implications of confirming DMS on K218b extend far beyond a single exoplanet. Sub-Neptunes like K218b are among the most common types of planets in our galaxy, making up a significant fraction of the worlds discovered by planet hunting missions. If these Hycean worlds can indeed support life, then habitable planets might be far more numerous than we ever imagined. Traditional searches for habitable exoplanets have focused on rocky worlds similar to Earth, orbiting sun-like stars at distances where liquid water could exist on their surfaces. But Hycean planets expand the definition of habitability to include a vast population of worlds that were previously overlooked. These hydrogen-wrapped ocean worlds could remain habitable even at distances where traditional rocky planets would be frozen solid. The greenhouse effect from their thick atmospheres might maintain liquid oceans under conditions that would be impossible for Earth-like worlds. This suggests that the habitable zone around every star might be much larger than we thought, potentially doubling or tripling the number of worlds where life could exist. The study of K218b is also revealing the incredible diversity that exists among planetary atmospheres. Each world we examine in detail shows us new possibilities for how atmospheric chemistry can work, expanding our understanding of what kinds of environments might support life. As we continue to peer deeper into the cosmos with increasingly sophisticated instruments, we're discovering that the universe is far stranger and more varied than our Earth-based perspective ever suggested. K218b represents just the beginning of this journey of discovery, a world that has already challenged our assumptions about habitability and might soon provide the answer to one of humanity's most profound questions. The challenges facing researchers studying K218b extend far beyond the technical difficulties of detecting molecules across interstellar distances. We're essentially trying to understand an entirely alien world using instruments designed based on our understanding of Earth's atmosphere and chemistry. It's like trying to decode a language where we only know a few words, and we're not even sure those words mean the same thing in different contexts. Consider the sheer audacity of what we're attempting here. We're taking light that left a distant star 124 years ago, light that has travelled through the vacuum of space for longer than any human has been alive, and we're using it to determine whether microscopic organisms might be floating in an alien ocean beneath a hydrogen sky. The precision required for this kind of analysis pushes our technology to its absolute limits. The atmospheric models used to interpret K218b's spectroscopic data rely heavily on our understanding of chemistry and physics as they operate under Earth-like conditions. But Hycean worlds represent environments so exotic that our terrestrial experience might be inadequate for understanding them. The pressures, temperatures, and chemical interactions occurring in K218b's atmosphere could create entirely new pathways for molecular formation and destruction. This uncertainty becomes particularly acute when we consider the concentrations of dimethyl sulfide potentially detected on K218b. The levels suggested by the preliminary data are thousands of times higher than anything we observe in Earth's atmosphere. If life is producing these molecules, it would have to be doing so on scales that dwarf the entire biomass of our planet's oceans. Dr. Eddie Schwieterman from UC Riverside, who studies biosignatures and atmospheric chemistry, has pointed out that such extreme concentrations raise important questions about the viability of the life hypothesis. On Earth, DMS is produced by phytoplankton in relatively small quantities and is quickly broken down by atmospheric chemistry. For K2-18b to maintain such high levels, either the production mechanisms would need to be extraordinarily efficient, or the destruction pathways would need to be severely limited. One possibility is that the unique chemistry of a hydrogen-dominated atmosphere might create conditions where DMS is more stable than it would be in an oxygen-rich environment like Earth's. Hydrogen atmospheres lack the highly reactive hydroxyl radicals that destroy many organic molecules in our atmosphere, potentially allowing biosignature gases to accumulate to much higher concentrations than we see on our own planet. Alternatively, the hydrogen-rich environment might enable entirely different biochemical pathways that could produce DMS through processes we've never encountered on Earth. Life has a remarkable ability to adapt to extreme environments, and the organisms that might exist in K2-18b's oceans could have evolved metabolisms unlike anything in our terrestrial experience. The possibility of false positives looms large in discussions about K2-18b's potential biosignature. The history of astrobiology is littered with promising discoveries that later turned out to have mundane explanations. The Viking missions to Mars in the 1976 detected what appeared to be biological activity in Martian soil samples, results that generated tremendous excitement before being explained by unexpected soil chemistry. More recently, the detection of phosphine in Venus's atmosphere sparked speculation about aerial microbes before alternative production mechanisms were proposed. These cautionary tales have shaped the astronomical community's approach to biosignature detection, creating a culture of healthy skepticism that demands multiple lines of evidence before extraordinary claims are accepted. The DMS detection on K2-18b, while intriguing, represents just one piece of what would need to be a much larger puzzle before scientists would be comfortable claiming the discovery of life. Part of the challenge lies in the inherent limitations of remote sensing. We can only observe K2-18b during the brief moments when it passes in front of its host star, and even then, we're analysing incredibly subtle changes in the star's light spectrum. These observations provide snapshots of the planet's atmospheric chemistry, but they can't tell us about temporal variations, spatial distributions, or the underlying processes driving chemical production. On Earth, biosignatures like DMS show complex patterns of variation across different seasons, locations, and ecological conditions. Marine phytoplankton blooms create temporary increases in DMS production, while changes in ocean temperature and chemistry affect the molecule's atmospheric lifetime. We have no way of knowing whether similar variations might be occurring on K2-18b, or how they might affect our ability to interpret the spectroscopic data. The research team led by Dr. Madhusudan has acknowledged these uncertainties, while maintaining cautious optimism about their findings. They've outlined specific follow-up observations that could strengthen or refute the DMS detection, including longer exposure times with James Webb's most sensitive instruments and observations at additional wavelengths that could provide independent confirmation of the molecule's presence. These future observations represent a critical test for the biosignature hypothesis. If DMS is indeed present in K2-18b's atmosphere at the levels suggested by the preliminary data, more extensive observations should be able to detect it with much higher statistical significance. Conversely, if the initial detection was a false positive, additional observations should fail to confirm the molecule's presence. The timeline for these follow-up observations depends on the complex scheduling of James Webb Space Telescope time, which is allocated through a competitive process involving research teams from around the world. K2-18b represents just one target among hundreds of high-priority objects that astronomers want to study with this revolutionary instrument. However, the potential significance of confirming or refuting a biosignature detection makes it likely that additional observing time will be allocated to this system. While we wait for those crucial follow-up observations, theoretical work continues on understanding how life might operate in Hycean environments. The conditions on K218b would be unlike anything experienced by terrestrial organisms, requiring life forms to adapt to high atmospheric pressures, hydrogen-rich chemistry, and potentially very different ocean compositions than Earth's seas. Some researchers have begun exploring whether Earth-based extremophiles, organisms that thrive in harsh environments, might provide clues about the kinds of life that could exist on Hycean worlds. Deep-sea bacteria that live near hydrothermal vents, microorganisms that survive in highly acidic or alkaline conditions, and archaea that thrive in high-pressure environments all demonstrate life's remarkable ability to adapt to conditions that would be lethal to most organisms. Laboratory experiments are being designed to test whether terrestrial microorganisms could survive and reproduce under conditions similar to those expected on K218b. These studies involve exposing bacteria and archaea to hydrogen-rich atmospheres, high pressures, and altered ocean chemistry to see if any Earth-based life forms might provide analogues for potential Hycean organisms. The results of these experiments could inform our interpretation of the K218b observations by providing insights into the kinds of metabolisms and biochemical pathways that might be possible under Hycean conditions. If terrestrial organisms can adapt to hydrogen-rich environments and produce molecules like DMS under those conditions, it would strengthen the biological interpretation of the spectroscopic data. The broader implications of discovering life on K218b extend far beyond astrobiology into fundamental questions about the nature and distribution of life in the universe. For decades, the search for extraterrestrial life has been guided by the principle of following the water, looking for worlds where liquid H2O might exist on planetary surfaces. The discovery of potentially habitable Hycean worlds would represent a paradigm shift in this approach. If life can indeed thrive in the hydrogen-wrapped oceans of sub-Neptune planets, then the number of potentially habitable worlds in our galaxy could increase by orders of magnitude. Sub-Neptunes are among the most common types of exoplanets, and red dwarf stars like K218's host are the most numerous stellar types in the Milky Way. The combination of abundant planets and abundant stars could mean that Hycean worlds represent the most common habitable environment in the galaxy. This possibility has profound implications for the Drake equation, the famous formula used to estimate the number of communicating civilizations in our galaxy. If Hycean worlds can support life, and if that life can evolve to intelligence and technology, then the universe might be far more populated than our Earth-centric perspective has suggested. The detection of life on K218b would also raise immediate questions about whether similar biosignatures might be detectable on other sub-Neptune exoplanets. Astronomers have already identified dozens of other sub-Neptunes orbiting in their stars' habitable zones, many of which could be suitable targets for biosignature searches with James Webb, and on multiple worlds would transform astrobiology from afield future telescopes. The prospect of finding life signatures focused on detecting life to one concerned with understanding the diversity and distribution of life throughout the cosmos. Each world would likely host unique ecosystems adapted to their specific atmospheric and oceanic conditions, creating a vast tapestry of biological diversity that we're only beginning to imagine. Yet even as we contemplate these extraordinary possibilities, the scientific community maintains its commitment to rigorous analysis and evidence-based conclusions. The potential DMS detection on K218b represents our most promising lead in the search for extraterrestrial life, but it remains just that, a lead that requires careful investigation and confirmation. The next few years will be crucial for determining whether K218b truly hosts the biosignatures that could indicate life, or whether these signals represent previously unknown chemical processes occurring in exotic atmospheric environments. Either outcome would advance our understanding of planetary atmospheres and the potential for life in the universe, but only one would answer the ancient question that has driven human curiosity since we first looked up at the stars and wondered if we were alone. As James Webb continues its observations, and as theoretical models become more sophisticated, we edge closer to answers that could fundamentally change our understanding of our place in the cosmos. K2-18b has already shown us that the universe is stranger and more diverse than we imagined, and it may yet reveal whether that strangeness includes the familiar chemistry of life itself. The story of how we arrived at this momentous discovery is as fascinating as the discovery itself. When the James Webb Space Telescope first locked on to K2-18b in its crosshairs, astronomers weren't expecting to stumble upon what might be the most significant finding in human history. They were simply conducting routine atmospheric characterization of an interesting sub-Neptune, part of a broader survey to understand how these common yet mysterious worlds differ from the planets in our own solar system. The observations themselves required extraordinary patience and precision. Unlike photographing a distant galaxy or nebula, studying an exoplanet's atmosphere demands perfect timing. Scientists had to wait for K2-18b to pass directly between its host star and Earth, an event called a transit that occurs only once every 33 days. Even then, the window of opportunity lasts mere hours as the planet crosses the face of its star. During those precious moments, James Webb collected photons that had travelled 124 light-years through the cosmos, light that had been filtered through K2-18b's atmosphere and carried within it the chemical signatures of that distant world. The data arrived as streams of numbers, wavelengths and intensities that meant nothing to the casual observer, but contained secrets that would keep atmospheric chemists busy for months. Dr. Madhusudan's team spent countless hours passing through this data, looking for the telltale absorption lines that would reveal which molecules existed in K2-18b's atmosphere. Each molecule has its own unique fingerprint in the infrared spectrum, like a cosmic barcode that identifies its presence. Water vapor shows up at specific wavelengths, carbon dioxide at others, and methane creates its own distinctive pattern of absorption lines. The initial results were encouraging, but not revolutionary. The detection of water vapor, while exciting, had been anticipated based on theoretical models of Hycean worlds. The presence of carbon dioxide and methane fitted neatly into expectations for this type of planet. The shortage of ammonia was actually good news, supporting the hypothesis that liquid oceans might exist beneath the hydrogen atmosphere. But then something unexpected appeared in the data. Hidden among the forest of absorption lines was a signal that didn't belong to any of the molecules they'd been expecting to find. At first, the researchers thought it might be an instrumental artifact or contamination from Earth's own atmosphere. Space-based telescopes can sometimes pick up trace amounts of terrestrial gases that cling to the spacecraft or outgas from its components. Yet as they dug deeper into the analysis, cross-referencing multiple observations and eliminating potential sources of error, the signal persisted. The wavelengths matched those expected for dimethyl sulfide, but the implications were so profound that the team spent months double and triple checking their work before even considering publication. The process of peer review added another layer of scrutiny to the findings. Independent researchers examined the data analysis methods, questioned the statistical techniques, and proposed alternative explanations for the observed signals. This rigorous vetting process, while sometimes frustrating for scientists eager to share their discoveries, represents one of the greatest strengths of modern science. Some reviewers suggested that the DMS signal might be contamination from other molecules with similar spectroscopic features. Others questioned whether the statistical significance was sufficient to support such an extraordinary claim. The research team addressed each concern methodically, refining their analysis and acknowledging the uncertainties that remained. The publication of their findings in a major astronomical journal marked the beginning rather than the end of the scientific process. Within days, research groups around the world began their own independent analyses of the publicly available data. Some confirmed the team's findings, while others expressed skepticism about the interpretation of the spectroscopic signals. This healthy scientific debate reflects the magnitude of what's at stake. The detection of a genuine biosignature would represent the most significant discovery in the history of science, fundamentally altering our understanding of life's prevalence in the universe. Such extraordinary claims naturally invite extraordinary scrutiny, and the scientific community has responded with appropriate caution and rigor. Meanwhile, theoretical work has begun to explore what life might actually look like on a world like K218b. The conditions there would be unlike anything in Earth's biosphere, presenting unique challenges and opportunities for any organisms that might call that world home. The atmospheric pressure at the ocean surface could be dozens of times greater than at Earth's sea level, creating an environment more similar to our deep ocean trenches than our familiar surface waters. The chemistry of a hydrogen-rich atmosphere would fundamentally alter the kinds of biochemical reactions that could occur. On Earth, oxygen plays a crucial role in many biological processes, from respiration to the formation of complex organic molecules. In K218b's hydrogen-dominated environment, life would need to find alternative pathways for energy production and molecular construction. Some researchers have proposed that life in such environments might actually have advantages over terrestrial organisms. The absence of highly reactive oxygen species could reduce cellular damage and potentially extend organism lifespans. The high atmospheric pressure might enable more efficient gas exchange between organisms and their environments. The vast oceans could provide enormous volumes of habitat space, potentially supporting ecosystems of unimaginable scale and diversity. The potential detection of DMS on K218b has also sparked renewed interest in understanding how this molecule behaves under exotic conditions. Laboratory experiments are being designed to test whether DMS can be produced through non-biological processes under the high-pressure, hydrogen-rich conditions that might exist on Hycean worlds. These experiments involve recreating the extreme conditions of K218b's atmosphere in specialized chambers, then exposing various chemical mixtures to see if DMS can form without biological intervention. The results could either strengthen the case for life by ruling out abiotic production pathways, or provide alternative explanations for the observed signals. Simultaneously, computational models are being developed to simulate the complex chemistry that might occur in K218b's atmosphere and oceans. These models attempt to account for the unique interactions between hydrogen-rich atmospheres and liquid water, exploring how molecules might form, react, and accumulate under conditions never before encountered in our solar system. The challenges facing these theoretical efforts are immense. We're essentially trying to predict the behavior of chemistry under conditions so extreme and exotic that we have no direct experience with them. It's like trying to understand the rules of a game we've never played, using equipment we've never seen, in an environment we've never visited. Yet these efforts are crucial for interpreting the observational data from K218b. Without theoretical frameworks to guide our understanding, we're left with intriguing signals, but no way to determine their significance. The interplay between observation and theory will ultimately determine whether we're looking at evidence for life or simply the signatures of exotic atmospheric chemistry. The technological requirements for studying worlds like K218b have pushed instrument development to new extremes. The precision needed to detect potential biosignatures across interstellar distances requires spectrographs that can measure wavelengths to accuracies of parts per billion. The stability needed to track subtle changes over multiple observations demands thermal control systems that maintain temperatures to within millikelvin. James Webb represents the current pinnacle of this technology, but even it struggles at the edges of what's needed for definitive biosignature detection. Future space telescopes are already being designed with even greater sensitivity and precision, instruments that could potentially detect biosignatures with the statistical confidence needed for scientific certainty. The extremely large telescopes currently under construction on Earth will complement space-based observations with their own unique capabilities. Their enormous mirrors will collect vast amounts of light, enabling detailed spectroscopic studies of exoplanet atmospheres with unprecedented resolution. The combination of space-based and ground-based observations could provide the multiple lines of evidence needed to confirm or refute potential biosignature detections. As we stand at this crossroads in human history, the implications extend far beyond astronomy and astrobiology. The discovery of life beyond Earth would fundamentally alter philosophy, religion, and our understanding of our place in the cosmic order. It would raise immediate questions about the nature of that life, its origins, and its relationship to terrestrial biology. Would life on K218b share a common ancestry with Earth's organisms, suggesting that life might have spread between worlds through some cosmic seeding process? Or would it represent an entirely independent genesis, proving that life is a natural consequence of chemistry under the right conditions? These questions would drive scientific inquiry for generations to come. The detection of life on K218b would also have profound implications for the search for intelligent life in the universe. If simple organisms can thrive in the exotic environments of Hycean worlds, what might be possible given millions or billions of years of evolution? Could intelligence emerge from such alien biospheres, leading to technological civilizations unlike anything we might imagine? These considerations have led some researchers to propose that we should be listening for signals from Hycean worlds, not just Earth-like planets. The SETI Institute and other organizations dedicated to the search for extraterrestrial intelligence are beginning to consider how their search strategies might need to evolve if life proves to be common on sub-Neptune exoplanets. The possibility of communicating with life on K218b, however, faces enormous practical challenges. The 124 light-year distance means that any signal would take nearly 2.5 centuries to make a round trip. Even if intelligent life existed on K218b and was actively trying to communicate with us, the conversation would unfold on timescales that dwarf human civilization. Yet the mere knowledge that life existed elsewhere would transform our species' perspective on existence itself. We would no longer be alone in the universe, no longer unique in our ability to contemplate the cosmos and our place within it. The implications would ripple through every aspect of human culture and understanding. Religious traditions would grapple with expanding their cosmologies to include life beyond Earth. Philosophers would debate what the discovery meant for concepts of purpose and meaning in the universe. Artists and writers would find new inspiration in imagining the possibilities of alien life and alternative biospheres. Education systems would need to incorporate astrobiology into their curricula, preparing future generations to live in a universe known to harbour life beyond Earth. The discovery would likely inspire unprecedented investment in space science and exploration as humanity sought to learn more about our cosmic neighbours and perhaps even develop technologies for interstellar travel. The economic implications would be substantial as well. The space industry would experience explosive growth as governments and private organisations invested in telescopes, spacecraft, and technologies needed to study distant worlds. New fields of research would emerge, creating career opportunities for scientists, engineers, and technicians specializing in astrobiology and exoplanet science. But perhaps most profoundly, the discovery of life on K218b would serve as a reminder of how much we still don't know about the universe we inhabit. Each answer we uncover seems to reveal 10 new questions, expanding rather than limiting the scope of cosmic mystery. As we await the results of future observations that will either confirm or refute the potential biosignature on K218b, we find ourselves balanced on the edge of what might be the greatest discovery in human history. The next few years could bring us face to face with the reality that we share this universe with other forms of life, fundamentally altering our understanding of what it means to be alive in this vast cosmos. The gentle light from a K218's host star continues its journey toward Earth, carrying within it the secrets of a world that might harbour life. Each photon that reaches our telescopes brings us closer to answering the question that has haunted humanity since we first looked up at the night sky and wondered if we were truly alone among the stars. The journey toward understanding K218b's potential for life has revealed just how much we're pushing the boundaries of what's scientifically possible with current technology. When astronomers first began analysing the spectroscopic data from this distant world, they quickly realised they were venturing into uncharted territory. The molecules they were hunting for existed at concentrations so low that detecting them was like trying to identify a whisper in a thunderstorm. The precision required for these measurements is almost incomprehensible. Imagine trying to measure the thickness of a human hair from the distance of a football field, and you begin to appreciate the technical challenges facing researchers studying K218b. The variations in starlight that carry information about the planet's atmospheric composition represent changes of just a few parts per million in the overall brightness of the host star. This extraordinary precision is possible only because of revolutionary advances in infrared detector technology and data processing algorithms. The sensors aboard James Webb are cooled to temperatures just a few degrees above absolute zero, reducing thermal noise to levels that would have been impossible to achieve with earlier generations of space telescopes. The data processing systems can identify and correct for subtle systematic errors that would completely overwhelm the tiny signals from distant exoplanet atmospheres. Yet even with these technological marvels, the detection of potential biosignatures on K218b required months of painstaking analysis. Research teams had to account for everything from cosmic ray hits on the detector to minute variations in the telescope's pointing stability. Each potential source of error had to be identified, modelled, and removed from the data before the true atmospheric signals could emerge. The complexity of this process becomes even more daunting when you consider that we're trying to understand an atmosphere unlike anything in our own solar system. The chemical interactions occurring in K218b's hydrogen-rich environment might follow pathways that have never been studied in terrestrial laboratories. The pressure and temperature conditions could enable molecular formations that are impossible under Earth-like conditions. Dr. Sarah Seeger from MIT, one of the pioneers of exoplanet atmospheric characterization, has described the challenge as trying to decode a message written in a language we're still learning to speak. Each spectroscopic line represents a word in that language, but the grammar and syntax of atmospheric chemistry on Hycean worlds might be fundamentally different from what we understand based on our terrestrial experience. This linguistic metaphor becomes particularly apt when considering the potential false positive scenarios that could explain the DMS detection. Just as words in different languages can sound similar while meaning completely different things, molecular absorption lines from different compounds can sometimes overlap in ways that create misleading signals. The research teams have had to carefully rule out dozens of alternative explanations for the spectroscopic features they've observed. One of the most challenging aspects of interpreting K218b's atmospheric data is the sheer number of variables at play. The planet's atmosphere is a complex dynamic system where temperature, pressure, and chemical composition vary with altitude, latitude, and time. The spectroscopic observations provide only a snapshot of this system, averaged over the entire visible disk of the planet and integrated over the few hours of transit observation. On Earth, atmospheric scientists use networks of weather stations, satellites, and aircraft to build three-dimensional maps of our atmosphere's structure and composition. They can track how concentrations of different gases change with season, weather patterns, and human activity. For K218b, all of this rich detail is compressed into a single spectrum that must somehow reveal the secrets of an entire world's atmospheric chemistry. The statistical methods used to extract information from such limited data have become increasingly sophisticated. Machine learning algorithms trained on vast databases of laboratory spectra can identify subtle patterns that human analysts might miss. Bayesian statistical techniques allow researchers to quantify the uncertainty in their measurements and compare the relative likelihood of different explanations for the observed signals. These advanced analytical methods have revealed surprising complexity in K218b's atmospheric composition. Beyond the headline-grabbing potential detection of DMS, the planet's spectrum contains hints of other molecules that could provide additional clues about conditions on this distant world. Trace amounts of sulfur-bearing compounds, organic molecules, and exotic chemical species paint a picture of atmospheric chemistry that is both alien and tantalizingly familiar. The sulfur chemistry of K218b's atmosphere has become a particular focus of research attention. On Earth, sulfur plays crucial roles in both biological and geological processes, cycling between the atmosphere, oceans, and crustal rocks through complex pathways that have evolved over billions of years. The detection of multiple sulfur-bearing molecules on K218b suggests that similar cycling might be occurring on this distant world. Though the specific mechanisms could be radically different, some researchers have proposed that the sulfur compounds detected on K218b might be produced by hydrothermal activity on the ocean floor, similar to the deep-sea vents that support unique ecosystems in Earth's oceans. These underwater volcanic systems could provide the chemical energy needed to drive biological processes, creating oases of life in the dark depths beneath K218b's hydrogen sky. The possibility of hydrothermal activity on K218b raises fascinating questions about the planet's internal structure and geological history. Unlike rocky planets like Earth, where plate tectonics and volcanic activity are driven by radioactive decay in the core, the internal dynamics of sub-Neptune planets remain largely mysterious. The enormous pressures created by K218b's massive atmosphere might compress the underlying ocean to such extremes that entirely new states of matter could exist at the interface between liquid and solid. Recent theoretical work has suggested that the cores of sub-Neptune planets might consist of exotic forms of ice that exist only under extreme pressure conditions. These superionic ices could conduct electricity like metals while maintaining the molecular structure of crystalline water. The interaction between such exotic core materials and the overlying ocean could drive chemical processes unlike anything seen on Earth. The magnetic field implications of these exotic internal structures are particularly intriguing. If K218b's core contains electrically conductive materials, the planet might generate a magnetic field that could protect its atmosphere from being stripped away by stellar radiation. Red dwarf stars like K218's host are known to produce powerful flares that could otherwise erode planetary atmospheres over geological timescales. The presence of a protective magnetic field would be crucial for maintaining the stable atmospheric chemistry needed to support life. Without such protection, any biosignature molecules produced by hypothetical organisms would be quickly destroyed by high-energy particles from the host star. The longevity of complex molecules in K2-18b's atmosphere might therefore provide indirect evidence for magnetic protection and, by extension, for internal geological activity. These considerations highlight how the search for life on K2-18b has evolved into a comprehensive study of planetary science across multiple disciplines. Understanding whether this world could support life requires insights from atmospheric chemistry, geology, magnetospheric physics, and astrobiology. Each piece of the puzzle must fit together coherently for the life hypothesis to remain viable. The interdisciplinary nature of this research has fostered unprecedented collaboration between scientists who might normally work in isolation. Atmospheric chemists are working alongside geologists to understand how surface-ocean interactions might affect gas concentrations. Magnetospheric physicists are collaborating with astrobiologists to model how stellar radiation might influence the survival of potential organisms. Computer scientists are developing new algorithms to extract maximum information from limited observational data. This collaborative approach has already yielded insights that extend far beyond K2-18b itself. The techniques developed for analyzing this planet's atmosphere are being applied to other exoplanet systems, creating a growing database of atmospheric compositions that reveals the incredible diversity of worlds beyond our solar system. Each new observation adds another data point to our understanding of how planetary atmospheres evolve and what conditions might be necessary for life to emerge and thrive. The comparative planetology approach has revealed that K2-18b, while unique in many ways, shares certain characteristics with other sub-Neptune exoplanets that orbit in their star's habitable zones. This growing sample of potentially habitable worlds is beginning to show patterns that could help us understand which factors are most important for creating conditions suitable for life. Some sub-Neptunes show clear evidence of water vapor in their atmospheres, while others appear to be dominated by heavier gases like carbon dioxide or methane. The differences might depend on factors like the planet's formation histories, their distances from their host stars, or the compositions of the disks from which they formed. Understanding these relationships could help us predict which newly discovered exoplanets are most likely to harbour biosignatures. The technological lessons learned from studying K2-18b are also informing the design of next-generation space telescopes that will push biosignature detection to even greater precision. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will complement James Webb with its own unique capabilities for exoplanet characterization. Ground-based facilities like the Extremely Large Telescope will provide unprecedented light-gathering power for detailed spectroscopic studies. These future instruments are being designed with the specific goal of achieving the statistical significance needed to definitively confirm biosignature detections. Where current observations might reach 3 sigma confidence levels, future telescopes could routinely achieve 5 sigma detections, providing the certainty needed to claim the discovery of life beyond Earth. The development of these advanced instruments represents a massive investment by the international scientific community in answering one of humanity's most profound questions. Government space agencies, private foundations, and international collaborations are dedicating billions of dollars to building the tools needed to detect life on distant worlds. This investment reflects not just scientific curiosity, but a recognition that such discoveries could fundamentally transform our understanding of our place in the universe. The potential implications of confirming life on K2-18b extend into realms that scientists are only beginning to explore. If life can emerge and thrive in the exotic conditions of Hycean worlds, What might billions of years of evolution produce on such planets? Could intelligence arise in hydrogen-wrapped oceans? Might technological civilizations develop under conditions so different from Earth that their technologies would be unrecognizable to us? These speculative questions have begun to influence how researchers approach the search for techno-signatures, observable evidence of alien technology. Traditional SETI efforts have focused on radio signals from civilizations similar to our own, but the discovery of potentially habitable Hycean worlds suggests that we might need to expand our search strategies to consider technologies adapted to very different environments. The possibility of life on K218b has also sparked new interest in theoretical biology and the fundamental requirements for living systems. Researchers are exploring whether the basic principles of evolution and natural selection might operate differently under the extreme conditions of Hycean worlds. The high atmospheric pressures, exotic chemistry, and vast ocean volumes could create evolutionary pressures unlike anything experienced by terrestrial life. Some theorists have proposed that life in Hycean environments might evolve toward gigantism, with organisms growing to sizes impossible on Earth due to the supportive effects of high atmospheric pressure. Others suggest that the stable, energy-rich environment of hydrogen-wrapped oceans might favor the evolution of extremely long-lived organisms, potentially leading to ecosystems that persist for geological timescales. The energy sources available to hypothetical life on K218b present another fascinating area of speculation. While Earth's biosphere is ultimately powered by solar energy captured through photosynthesis, the thick hydrogen atmosphere of a Hycean world might severely limit the amount of stellar radiation reaching the ocean surface. Life there might need to rely instead on chemical energy sources, similar to the chemosynthetic organisms that thrive around Earth's deep-sea hydrothermal vents. The chemistry of a hydrogen-rich ocean could provide abundant opportunities for chemosynthetic metabolism. The interaction between hydrogen gas and dissolved sulfur compounds could drive chemical reactions that release energy suitable for biological processes. The high pressures might enable chemical pathways that are thermodynamically unfavorable under Earth-like conditions, potentially supporting metabolisms that would be impossible in our biosphere. These theoretical explorations help scientists understand what kinds of biosignatures might be produced by life adapted to Hycean conditions. If organisms on K218b rely primarily on sulfur-based metabolism, they might produce different combinations of gases than Earth's primarily carbon and oxygen-based biosphere. Understanding these alternative biochemistries is crucial for interpreting the atmospheric observations and determining whether the detected molecules truly indicate biological activity. The search for life on K218b has also highlighted the importance of understanding false positive scenarios, situations where natural geological or atmospheric processes might mimic the signatures of biological activity. The solar system provides several examples of how non-biological processes can produce molecules that might otherwise be interpreted as biosignatures. Jupiter's moon, Europa, for example, produces hydrogen peroxide through radiolytic processes as high-energy particles from Jupiter's magnetosphere interact with the moon's ice surface. Similar processes might occur on K218b, where stellar radiation and cosmic rays could drive chemical reactions that produce complex organic molecules without any involvement of living organisms. The volcanic activity on Io, another of Jupiter's moons, demonstrates how geological processes can produce sulfur compounds in concentrations that far exceed what biological processes typically generate. If K218b has active geology, similar volcanic processes might explain the sulfur chemistry observed in its atmosphere without requiring biological explanations. These considerations underscore the complexity of definitively identifying biosignatures in exoplanet atmospheres. Each potential detection must be evaluated not just for its statistical significance, but for its biological plausibility and the availability of alternative explanations. The scientific method demands that researchers exhaust all possible non-biological explanations before concluding that life is the most likely cause of observed phenomena. The ongoing analysis of K218 Habitable atmospheric data continues to refine our understanding of what these observations might mean. Each new paper published on this system adds nuance to our interpretation, sometimes strengthening the case for biological activity and sometimes suggesting alternative explanations. This iterative process of hypothesis testing and refinement is exactly how science should work when grappling with questions of such profound importance. The international nature of this research effort has been remarkable to witness. Teams from dozens of countries have contributed observations, analysis techniques, and theoretical insights to understanding K218b. The data from James Webb is publicly available, allowing researchers worldwide to conduct their own independent analyses and contribute to the growing body of knowledge about this fascinating world. This open science approach has accelerated progress and ensured that multiple perspectives are brought to bear on interpreting the observations. When different research groups using different analytical methods reach similar conclusions, it increases confidence in the results. When they disagree, it identifies areas where further work is needed to resolve uncertainties. The collaborative spirit of K218b research reflects the recognition that discovering life beyond Earth would be an achievement for all humanity, not just the specific scientists involved in the detection. The implications would be so profound that they would affect every human being, regardless of their nationality, profession, or personal beliefs. As we stand at this pivotal moment in the search for extraterrestrial life, the observations of K218b represent our best current hope for answering the age-old question of whether we are alone in the universe. The potential detection of dimethyl sulfide in this world's atmosphere has brought us tantalizingly close to what could be the most significant discovery in human history. The coming months and years will be crucial for determining whether this potential biosignature represents genuine evidence of life or simply reflects our incomplete understanding of atmospheric chemistry under exotic conditions. Either outcome will advance our knowledge and prepare us for future discoveries as our observational capabilities continue to improve. In the quiet moments between observations, as James Webb continues its patient watch over the cosmos, we find ourselves balanced between profound uncertainty and extraordinary possibility. The universe has surprised us before with its complexity and diversity, and K218b may yet hold the greatest surprise of all, the confirmation that life has found a way to flourish in the hydrogen-wrapped oceans of a world unlike any in our solar system. The gentle light from this distant world continues its ancient journey toward Earth, carrying within its spectral lines the secrets that could transform our understanding of life's place in the cosmic order. Each photon that reaches our detectors brings us closer to an answer that has eluded humanity throughout our entire existence as a species, the answer to whether we truly share this vast universe with other forms of life. The debate surrounding K218b's potential biosignature has revealed something fascinating about the nature of scientific discovery itself. We're witnessing science in action, watching as researchers around the world grapple with data that could either represent the most mundane atmospheric chemistry or the most extraordinary discovery in human history. The process is messy, contentious, and absolutely riveting. Dr. Madhusudan's team has faced criticism from colleagues who argue that the statistical significance of their DMS detection falls short of the rigorous standards required for such an extraordinary claim. The 3 sigma confidence level, while impressive for most astronomical observations, seems almost inadequate when weighed against the profound implications of discovering life beyond Earth. It's like being asked to bet the future of human understanding on a coin flip that lands heads 997 times out of 1,000. Yet this is precisely how science advances at the frontiers of human knowledge. Every revolutionary discovery begins with observations that push against the boundaries of what our instruments can detect and what our theories can explain. The initial detection of gravitational waves faced similar skepticism before additional observations confirmed Einstein's predictions. The discovery of dark energy emerged from observations that seemed to contradict our understanding of cosmic expansion before being accepted as evidence for a previously unknown force. The researchers studying K218b find themselves in a peculiar position, simultaneously hopeful and skeptical about their own findings. They've spent years developing the expertise needed to extract meaningful signals from the noise of interstellar observations, yet they're the first to acknowledge the limitations and uncertainties in their data. This intellectual honesty reflects the best traditions of scientific inquiry, where researchers must balance enthusiasm for discovery with rigorous self-criticism. The pressure surrounding K218b research extends beyond normal academic scrutiny. The potential for discovering life beyond Earth has captured public imagination in ways that more routine astronomical discoveries cannot match. Media outlets worldwide have covered the story, often with headlines that strain the boundaries between responsible reporting and sensationalism. The researchers find themselves navigating not just scientific challenges, but also the complex dynamics of public communication and expectation management. This public attention, while sometimes uncomfortable for scientists accustomed to working in relative obscurity, serves an important purpose in advancing our understanding of the cosmos. The excitement generated by potential biosignature detections helps justify the enormous public investments in space telescopes and astronomical research. It reminds us why we build billion-dollar instruments and point them at distant worlds, searching for answers to questions that define our place in the universe. The K218b observations have also revealed the incredible sophistication required for modern astronomical research. The data analysis pipelines used to process James Webb observations represent some of the most advanced signal processing techniques ever developed. These systems must account for everything from minute thermal variations in the telescope structure to the subtle effects of cosmic radiation on the detectors. Each observation of K218b generates terabytes of data that must be carefully calibrated, processed, and analyzed before meaningful scientific conclusions can be drawn. The raw data bears little resemblance to the elegant spectroscopic plots that appear in research papers. Instead, it consists of millions of individual measurements, each carrying a tiny piece of information about the distant world's atmospheric composition. The transformation of this raw data into scientific knowledge requires expertise spanning multiple disciplines. Instrument specialists understand how the telescope's various components affect the collected light. Atmospheric physicists model how different molecules absorb infrared radiation. Statisticians develop methods for extracting meaningful signals from noisy data. Computer scientists create algorithms capable of processing vast datasets efficiently. This collaborative effort reflects the increasing complexity of modern astronomy, where individual researchers must rely on teams of specialists to tackle questions that would have been impossible to address just decades ago. The detection of potential biosignatures on distant exoplanets represents perhaps the ultimate expression of this collaborative approach, requiring humanity's most advanced technologies and our deepest understanding of physics, chemistry, and biology. The implications of the K218b research extend far beyond the specific question of whether life exists on this particular world. The techniques developed for analysing its atmosphere are being applied to dozens of other potentially habitable exoplanets, creating an unprecedented survey of atmospheric diversity among worlds that might support life. Each new observation adds to our understanding of how planetary atmospheres evolve and what conditions might be necessary for biological processes to emerge and persist. The growing catalogue of exoplanet atmospheric compositions is revealing patterns that could help us understand the fundamental requirements for habitability. Some worlds show clear evidence of water vapour, while others appear dry despite orbiting in their stars' habitable zones. The differences might reflect varying formation histories, different stellar environments, or simply the natural diversity that emerges from the complex processes of planetary evolution. This comparative approach to exoplanet science mirrors the methods that revolutionized our understanding of planetary formation within our own solar system. By studying the diverse worlds orbiting our Sun, from the hellish surface of Venus to the methane lakes of Titan, scientists developed theories that could explain how planets form and evolve under different conditions. The extension of this approach to exoplanets is providing insights into planetary processes operating on scales and under conditions impossible to study within our local cosmic neighbourhood. The search for biosignatures on K218b and similar worlds is also driving advances in laboratory science that have applications far beyond astronomy. Understanding how molecules behave under the extreme conditions found on Hycean worlds requires experimental techniques that push the boundaries of high-pressure chemistry and physics. The results of these experiments inform not just our interpretation of exoplanet observations, but also our understanding of fundamental chemical processes under conditions that might exist deep within planetary interiors. Some of the most intriguing aspects of K218b's atmospheric chemistry involve reactions that simply cannot occur under Earth-like conditions. The combination of high pressures, hydrogen-rich chemistry, and potentially exotic ocean compositions could enable molecular processes that have never been observed in terrestrial laboratories. Understanding these processes requires developing new experimental techniques and theoretical frameworks that expand our basic knowledge of chemistry and physics. The potential biological implications of these exotic chemical processes are particularly fascinating. Life on Earth has evolved to exploit the specific chemical and physical conditions found in our planet's biosphere, but the fundamental principles of biology might operate very differently under the conditions found on Hycean worlds. The high atmospheric pressures could enable biological processes that would be impossible under Earth-like conditions, while the hydrogen-rich chemistry could provide energy sources unavailable to terrestrial organisms. Researchers studying extremophiles on Earth have discovered organisms that thrive under conditions once thought incompatible with life. Bacteria living in highly acidic hot springs, archaea thriving in salt concentrations that would be lethal to most organisms, and microbes surviving in the high-pressure environments of deep ocean trenches all demonstrate life's remarkable ability to adapt to extreme conditions. These discoveries provide hints about what might be possible in the even more extreme environments of distant exoplanets. The study of terrestrial extremophiles has become crucial for interpreting potential biosignature detections on worlds like K218b. If Earth-based organisms can survive and reproduce under conditions similar to those found on Hycean worlds, it strengthens the case that life might indeed be possible on these distant planets. Conversely, if no terrestrial organisms can tolerate Hycean-like conditions, it suggests that any life on such worlds would need to be fundamentally different from anything in Earth's biosphere. Laboratory experiments designed to test the limits of terrestrial life under Hycean conditions are yielding surprising results. Some microorganisms show remarkable resilience when exposed to high-pressure hydrogen atmospheres, maintaining metabolic activity under conditions that would quickly kill most familiar organisms. These findings suggest that the boundary between habitable and uninhabitable conditions might be more flexible than previously thought. The implications extend beyond individual organisms to entire ecosystem dynamics. If life can indeed thrive under Hycean conditions, the resulting ecosystems might operate according to principles very different from those governing Earth's biosphere. The energy sources, nutrient cycles, and evolutionary pressures would all be alien to our terrestrial experience, potentially leading to forms of biological organization unlike anything we've encountered. The possibility of discovering such alien ecosystems raises profound questions about our methods for detecting and characterizing life beyond Earth. Current biosignature research focuses primarily on molecules and processes familiar from terrestrial biology. But truly alien life might produce chemical signatures that we wouldn't recognize as biological. The challenge becomes not just detecting life, but recognizing it when it operates according to principles we've never encountered. This recognition problem becomes particularly acute when considering the potential for false negatives in biosignature searches. While much attention focuses on false positives, situations where natural processes mimic biological signatures, the opposite scenario might be equally problematic. If alien life produces biosignatures, unlike anything in our terrestrial experience, we might overlook genuine evidence of biological activity simply because it doesn't match our expectations. The K2-18b observations have highlighted this challenge by revealing atmospheric chemistry that doesn't fit neatly into either biological or non-biological categories. The unusual concentrations and combinations of molecules detected in the planet's atmosphere could represent either exotic life forms or previously unknown atmospheric processes. Distinguishing between these possibilities requires expanding our theoretical frameworks to encompass phenomena beyond our current understanding. This expansion of scientific understanding represents one of the most exciting aspects of exoplanet research. Each new world we study reveals possibilities we hadn't previously considered, forcing us to question assumptions and develop new theories to explain observations that don't fit existing models. The process mirrors the great revolutions in scientific thinking that have periodically transformed our understanding of the natural world. The study of K2-18b is also revealing the importance of long-term monitoring in understanding exoplanet atmospheres. Unlike the static chemical compositions we might assume from single observations, planetary atmospheres are dynamic systems that can change dramatically over time. Weather patterns, seasonal variations, and geological activity all influence atmospheric chemistry in ways that single transit observations might miss. The brief glimpses we get of exoplanet atmospheres during transit events provide snapshots of complex, evolving systems. Understanding whether observed chemical signatures represent stable atmospheric conditions or temporary phenomena requires multiple observations spread across months or years. This temporal aspect of atmospheric characterization adds another layer of complexity to interpreting potential biosignature detections. Future observations of K2-18b will need to address these temporal questions while also improving the statistical significance of potential biosignature detections. The observing strategies being developed for follow-up studies represent careful compromises between the desire for immediate answers and the need for comprehensive characterization. Each observation requires precious telescope time that could be used to study other potentially habitable worlds, forcing researchers to balance breadth and depth in their investigation strategies. The scheduling challenges facing K2-18b research reflect broader issues in modern astronomy, where demand for advanced telescope time far exceeds availability. The James Webb Space Telescope receives observation proposals requesting many times more hours than the instrument can provide, forcing review committees to make difficult decisions about which projects deserve priority. The potential significance of biosignature detections gives K218b researchers strong claims on telescope time, but it must compete with other groundbreaking research across all areas of astronomy and astrophysics. This competition for observational resources has fostered innovation in observation planning and data analysis techniques. Researchers are developing methods to extract maximum information from limited observing time, using advanced statistical techniques and machine learning algorithms to squeeze every possible insight from hard-won observations. The constraints imposed by telescope scheduling have paradoxically accelerated advances in data analysis that benefit all areas of astronomical research. The technological demands of studying worlds like K218b are also driving the development of next-generation space telescopes specifically designed for exoplanet characterization. These future instruments will address many of the limitations that currently constrain biosignature searches, providing the sensitivity and stability needed for definitive detections of life beyond Earth. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will complement James Webb with capabilities optimized for different aspects of exoplanet research. While James Webb excels at detailed atmospheric characterization of known exoplanets, Roman will survey vast areas of sky to discover new worlds and identify the most promising targets for follow-up studies. The synergy between these instruments could revolutionize our ability to find and characterize potentially habitable worlds. Ground-based telescopes are also evolving to meet the challenges of exoplanet atmospheric studies. The extremely large telescopes currently under construction will provide unprecedented light-gathering power and resolution, enabling detailed spectroscopic studies that complement space-based observations. The combination of space and ground-based capabilities could provide the multiple lines of evidence needed to definitively confirm biosignature detections. These technological advances represent massive investments by the international scientific community in answering fundamental questions about life in the universe. Government space agencies, international collaborations, and private organizations are dedicating billions of dollars to building the tools needed to detect and characterize life on distant worlds. The investments reflect not just scientific curiosity, but recognition that such discoveries could fundamentally transform our understanding of our place in the cosmos. The potential return on these investments extends far beyond astronomy into areas that could benefit all of human society. The technologies developed for detecting trace gases in exoplanet atmospheres have applications in environmental monitoring, medical diagnostics, and industrial process control. The data analysis techniques pioneered for astronomical research are finding uses in fields ranging from finance to healthcare. The international collaborations fostered by major space missions create relationships that facilitate cooperation on other global challenges. Yet the ultimate value of discovering life beyond Earth cannot be measured in technological spin-offs or economic benefits. Such a discovery would represent a fundamental expansion of human knowledge that would influence how we understand ourselves and our relationship to the universe. The psychological and philosophical implications would ripple through every aspect of human culture, from science and religion to art and literature. The ongoing research into K218b's potential biosignatures continues to generate both excitement and controversy within the scientific community. Each new analysis of the available data seems to reveal additional complexity rather than providing definitive answers. The atmosphere of this distant world appears to be far more intricate than initial observations suggested, with chemical processes that don't fit neatly into existing theoretical frameworks. The complexity itself might be the most important discovery emerging from K218b research. The assumption that exoplanet atmospheres would be relatively simple systems governed by well-understood physics and chemistry is proving naive as observations reveal the incredible diversity and sophistication of atmospheric processes operating on distant worlds. Each new detection challenges our theoretical models and forces us to expand our understanding of what's possible in planetary atmospheric chemistry. This expansion of knowledge represents the essence of scientific discovery, the gradual push against the boundaries of human understanding that has driven progress throughout history. Whether K218b ultimately proves to harbour life or simply represents an exotic example of atmospheric chemistry, the research has already advanced our knowledge in ways that will influence science for generations to come. The techniques developed, the theoretical frameworks expanded, and the questions raised will guide future investigations into the cosmic prevalence of life and the incredible diversity of worlds that populate our galaxy. As we await the results of future observations that may finally resolve the mystery of K218b's atmospheric chemistry, we find ourselves participants in one of humanity's greatest adventures. The search for life beyond Earth represents the culmination of centuries of scientific advancement and the beginning of what might be an even more extraordinary chapter in human understanding. In the quiet spaces between observations, as our most sophisticated instruments continue their patient watch over the cosmos, we balance on the threshold of discoveries that could transform everything we thought we knew about life's place in the universe. The statistical dance between certainty and possibility continues to unfold in laboratories and observatories around the world, where teams of researchers are conducting some of the most sophisticated analyses ever attempted in astronomy. The 3 sigma detection of dimethyl sulfide on K218b represents more than just a number on a statistical chart. It embodies the razor's edge between revolutionary discovery and scientific caution, between the extraordinary and the merely unusual. Consider what 3 sigma actually means in practical terms. If you were to repeat the same observation 1,000 times under identical conditions, you would expect to see a false positive signal only 3 times. In most fields of science, this level of confidence would be considered rock solid, sufficient to publish results and move forward with additional research. But when the implications are as profound as the discovery of life beyond Earth, the scientific community demands an even higher standard. The 5 sigma threshold that researchers are striving to reach would reduce the probability of a false positive to less than 1 in 3 million. It's the same standard that particle physicists demanded before announcing the discovery of the Higgs boson, recognizing that extraordinary claims require extraordinary evidence. The question facing K218b researchers is whether they can accumulate enough observational data to cross this statistical finish line. The path toward 5 sigma confidence requires more than simply pointing telescopes at K218b for longer periods. The researchers must also contend with systematic errors, instrumental artifacts, and the inherent limitations of studying a world that exists at the very edge of our technological capabilities. Each additional observation must be carefully planned to maximize the scientific return while minimizing the potential for contamination or misinterpretation. Dr. Madhusudan's team has outlined a specific roadmap for achieving this higher level of statistical confidence. They've identified particular wavelength ranges where the DMS signature should be strongest, instruments that provide the best sensitivity for detecting this molecule, and observational strategies that could eliminate alternative explanations for the observed signals. The plan requires between 16 and 24 hours of additional James Webb observations, a substantial allocation of one of humanity's most precious scientific resources. The competition for James Webb observing time reflects the telescope's revolutionary impact on multiple areas of astronomy. While exoplanet atmospheric characterization represents just one of the instrument's scientific capabilities, the potential for detecting biosignatures has generated intense interest from researchers worldwide. The telescope's schedule is booked months in advance, with hundreds of research teams competing for access to its unprecedented capabilities. This scheduling challenge has forced the astronomical community to develop new frameworks for prioritizing observations based on their potential scientific impact. Discovering life beyond Earth would rank among the most significant achievements in human history, but so would detecting the first galaxies formed after the Big Bang or characterizing the atmospheres of planets in our own solar system. The committees responsible for allocating telescope time must weigh these competing priorities while ensuring that resources are used efficiently. The international nature of James Webb operations adds another layer of complexity to observation planning. The telescope was built through a partnership between NASA, the European Space Agency, and the Canadian Space Agency, with each organisation contributing expertise, funding, and guaranteed observing time. Coordinating observations across multiple time zones and organisational structures requires careful planning and diplomatic skill that rivals the technical challenges of operating the instrument itself. Yet the potential rewards of confirming biosignatures on K218b justify the enormous effort being invested in these than just the discovery of life beyond Earth observations. The detection would represent more. It would validate an entirely new approach to searching for habitable worlds, one that expands the definition of habitability far beyond the traditional focus on Earth-like planets orbiting Sun-like stars. The implications for astrobiology would be transformative. If life can thrive in the hydrogen-wrapped oceans of Hycean worlds, then the number of potentially habitable planets in our galaxy could increase by orders of magnitude. Sub-Neptune planets like K218b are among the most common types of worlds discovered by planet-hunting missions, and red dwarf stars like its host are the most numerous stellar types in the Milky Way. The combination suggests that habitable environments might be far more prevalent than our Earth-centric perspective has led us to believe. This statistical revolution in habitability estimates would have profound implications for the famous Drake equation, the framework that astronomers use to estimate the number of communicating civilizations in our galaxy. If Hycean worlds can support life, and if that life can evolve toward intelligence and technology, then the universe might be far more populated than we've dared to imagine. The silence we've encountered in our searches for extraterrestrial intelligence might reflect limitations in our search strategies, rather than the absence of technological civilizations. The possibility of widespread life in Hycean environments is already influencing how researchers approach the search for techno-signatures, observable evidence of alien technology. Traditional SETI efforts have focused on radio signals from civilizations presumed to be similar to our own, but the discovery of potentially habitable sub-Neptune worlds suggests that technological species might develop under conditions radically different from those on Earth. Civilizations that evolved in the high-pressure, hydrogen-rich environments of Hycean worlds might develop technologies that operate according to principles unfamiliar to us. Their methods of communication, energy production, and space travel could be so different from our own that we might not recognize them as artificial. This recognition problem poses fundamental challenges for techno-signature research that extend far beyond traditional radio astronomy. The search for artificial signals from K218b itself presents unique challenges. The 124 light-year distance means that any communication would require nearly 2.5 centuries for a round trip, making real-time conversation impossible across human timescales. Even if intelligent life existed on the planet and was actively trying to communicate with us, the dialogue would unfold across time periods that exceed the lifespan of entire civilizations. Yet the mere knowledge that life existed on K218b would fundamentally alter our species' relationship with the cosmos. We would no longer be alone in the universe, no longer unique in our capacity for consciousness and technological development. The psychological impact would rival the Copernican revolution that displaced Earth from the center of the universe, forcing humanity to reconceptualize our place in the cosmic order. The cultural implications would be equally profound. Religious traditions would grapple with expanding their cosmologies to include life that developed under conditions unlike anything described in their foundational texts. Philosophers would debate whether consciousness and intelligence represent inevitable outcomes of cosmic evolution or remarkable accidents that occur only under specific circumstances. Artists and writers would find inspiration in imagining the possibilities of life forms adapted to environments beyond our terrestrial experience. Educational systems would face the challenge of preparing students for a universe known to harbour multiple forms of life. The discovery would likely inspire unprecedented investment in science education, as societies recognised the need for citizens capable of understanding and contributing to humanity's expanded cosmic perspective. New fields of study would emerge, combining astrobiology, comparative planetology, and xenopsychology in ways that don't currently exist. The economic implications would be substantial as well. The space industry would experience explosive growth as governments and private organizations invested in telescopes, spacecraft, and technologies needed to study other, potentially inhabited worlds. The confirmation of life on K218b would transform astrobiology from a speculative field into a practical science with immediate applications for understanding and potentially communicating with alien life forms. Research and development programs would focus on developing technologies for detailed study of distant biospheres, potentially including interstellar missions to nearby habitable worlds. While the enormous distances involved would make such missions extraordinarily challenging, the knowledge that life existed on accessible targets would justify investments in revolutionary propulsion technologies and autonomous spacecraft systems. The biotechnology industry would also experience transformation as researchers sought to understand how life might operate under conditions radically different from those on Earth. The study of extremophiles would expand to include laboratory simulations of Hycean environments, potentially revealing new biochemical pathways and molecular processes with applications in medicine, agriculture, and industrial biotechnology. Yet perhaps the most significant impact would be on human consciousness itself. The confirmation of life on K218b would serve as a cosmic mirror, reflecting back to us the remarkable nature of our own existence, while simultaneously demonstrating that life is not unique to our small corner of the universe. The discovery would be both humbling and inspiring, reminding us of our cosmic insignificance while celebrating the extraordinary phenomenon of life itself. The ongoing analysis of K218b's atmospheric data continues to reveal new layers of complexity that challenge our understanding of planetary atmospheric chemistry. Each refinement of the analytical techniques seems to uncover additional molecular species and chemical processes that don't fit neatly into existing theoretical frameworks. The planet's atmosphere is emerging as a far more dynamic and sophisticated system than initial observations suggested. Recent reanalysis of the spectroscopic data has identified potential signatures of additional organic molecules beyond the headline-grabbing DMS detection. Trace amounts of complex hydrocarbons, sulfur-bearing compounds, and nitrogen-containing species paint a picture of atmospheric chemistry that rivals Earth's biosphere in its complexity. Whether these molecules represent biological activity or exotic abiotic processes remains an open question that drives continued research. The isotopic ratios of various atmospheric constituents provide another avenue for understanding K218b's chemistry and potential biology. On Earth, biological processes often preferentially incorporate lighter isotopes, creating distinctive signatures that can be detected in atmospheric samples. Similar isotopic fractionation on K218b could provide additional evidence for biological activity, though interpreting such signals requires understanding how isotopic processes might operate under Hycean conditions. The challenge of isotopic analysis becomes particularly acute when dealing with spectroscopic observations across interstellar distances. The precision required to detect isotopic variations in exoplanet atmospheres pushes current instrumental capabilities to their absolute limits. Future generations of space telescopes will need even greater sensitivity and resolution to routinely perform such measurements on distant worlds. The temporal aspects of K218b's atmospheric chemistry add yet another dimension to the interpretive challenges facing researchers. The planet's 33-day orbital period means that conditions in its atmosphere might vary significantly depending on the planet's position relative to its host star. Seasonal variations, if they exist, could influence chemical production and destruction rates in ways that affect the interpretation of individual transit observations. Understanding these temporal variations requires multiple observations spread across the planet's orbital period and potentially across multiple years. Such long-term monitoring campaigns represent major investments of telescope time, but they could provide crucial insights into the stability and persistence of potential biosignature molecules in the planet's atmosphere. The detection of time-variable signals could actually strengthen the biological interpretation, as life often produces cyclical patterns in atmospheric chemistry. The three-dimensional structure of K218b's atmosphere represents another frontier in our understanding of this distant world. Current observations provide information averaged across the entire visible disk of the planet during transit events, but the actual atmospheric composition likely varies significantly with altitude, latitude, and local atmospheric conditions. Future observational techniques might be able to map these variations, providing much more detailed pictures of atmospheric structure and chemistry. Advanced modelling efforts are beginning to explore how atmospheric dynamics might influence the distribution and behaviour of potential biosignature molecules on K218b. The planet's thick hydrogen atmosphere could support complex circulation patterns driven by solar heating and the planet's rotation. These atmospheric motions could transport chemical species between different regions of the atmosphere, creating spatial variations in composition that might be detectable with sufficiently sensitive observations. The magnetic field environment around K218b remains largely unknown, but could play a crucial role in protecting any potential biosphere from harmful stellar radiation. Red dwarf stars are known for their powerful flare activity, which could strip away planetary atmospheres over geological timescales if not deflected by strong magnetic fields. The persistence of complex atmospheric chemistry on K218b might itself provide indirect evidence for magnetic protection. Theoretical studies of magnetic field generation in sub-Neptune planets suggest that these worlds could indeed produce strong magnetospheres if their interiors contain electrically conductive materials. The exotic forms of water ice that might exist under the extreme pressures in K218b's interior could have electrical properties very different from ordinary ice, potentially enabling magnetic dynamo processes unlike anything seen in our solar system. The interaction between K218b's potential magnetic field and its thick hydrogen atmosphere could create unique chemical environments that don't exist anywhere else in our cosmic neighbourhood. Charged particles trapped in magnetic field lines could drive chemical reactions that produce or destroy biosignature molecules through pathways that haven't been studied in terrestrial laboratories. Understanding these processes is crucial for interpreting observations and distinguishing between biological and purely physical explanations for atmospheric chemistry. The search for additional Hycean worlds in the K218 system has begun as astronomers recognize that planetary systems often contain multiple worlds with similar characteristics. If K218b formed under conditions that enabled it to develop a hydrogen-rich atmosphere and potential ocean, other planets in the same system might have followed similar evolutionary pathways. Discovering multiple potentially habitable worlds around a single star would provide valuable comparative data for understanding Hycean planet formation and evolution. The techniques developed for studying K218b are already being applied to other sub-Neptune exoplanets that orbit in their stars' habitable zones. Each new world studied adds to our growing understanding of atmospheric diversity among these mysterious planets. Some show clear evidence of water vapor and complex chemistry, while others appear to have much simpler atmospheric compositions. The differences might reflect varying formation histories, stellar environments, or simply the natural diversity that emerges from planetary evolution processes. Comparative studies of multiple Hycean candidates are beginning to reveal patterns that could help predict which newly discovered exoplanets are most likely to harbour biosignatures. Factors such as planetary mass, orbital distance, stellar age, and system architecture all appear to influence atmospheric composition in ways that researchers are only beginning to understand. This growing knowledge base will be crucial for prioritizing future observations as more potentially habitable worlds are discovered. The interdisciplinary nature of K218. B research continues to foster collaboration between fields that rarely interact in traditional academic settings. Atmospheric chemists are working with marine biologists to understand how life might adapt to high-pressure aquatic environments. Geophysicists are collaborating with astrobiologists to model the internal structures of sub-Neptune planets. Computer scientists are developing machine learning algorithms specifically designed to identify subtle biosignature signals in noisy spectroscopic data. This cross-pollination of expertise is generating insights that no single discipline could achieve alone. The study of K218b has become a proving ground for interdisciplinary scientific collaboration, demonstrating how complex questions require diverse perspectives and expertise. The success of this collaborative approach is influencing how major scientific institutions organize research efforts and allocate resources for addressing other grand challenges. The educational impact of K218. B research extends beyond traditional academic boundaries into public engagement and science communication. The potential for discovering life beyond Earth has captured public imagination in ways that more routine astronomical discoveries cannot match. Science museums, planetariums, and educational institutions worldwide are incorporating the K218b story into programs designed to inspire interest in science and space exploration. The challenge for science educators is communicating the uncertainty and complexity of the research process while maintaining public engagement and excitement. The story of K218b perfectly illustrates how science works at the frontiers of human knowledge, where observations challenge existing theories and force researchers to expand their understanding. Teaching these concepts helps prepare students for a world where scientific knowledge continues to evolve and expand in response to new discoveries. The global nature of K218. B. Research has created opportunities for international collaboration that extend far beyond the specific scientific questions being addressed. Researchers from dozens of countries are contributing observations, analytical techniques, and theoretical insights to understanding this distant world. The collaborative networks established for this research are being leveraged for other major scientific projects that require international coordination and resource sharing. These international partnerships demonstrate how fundamental scientific questions can unite researchers across political and cultural boundaries. The search for life beyond Earth represents a common human endeavour that transcends national interests and ideological differences. The collaborative spirit fostered by projects like K218b research could serve as a model for addressing other global challenges that require sustained international cooperation. As we continue our patient vigil for additional observations that might definitively resolve the mystery of K218b's atmospheric chemistry, we find ourselves participants in one of the most significant scientific endeavours in human history. Whether the planet ultimately proves to harbour life or simply represents an exotic example of atmospheric chemistry, the research has already transformed our understanding of what's possible in the universe and demonstrated humanity's remarkable capacity for pushing the boundaries of knowledge. The gentle light from K218's host star continues its ancient journey toward Earth, carrying within its spectral signatures the potential answers to questions that have defined human curiosity since our species first developed the capacity for wonder. Each photon that reaches our detectors represents a messenger from a world so distant and alien that its very existence challenges our assumptions about the nature of life and habitability in the cosmos. In the quiet moments between observations, as our most sophisticated instruments maintain their patient watch over this distant world, we stand balanced between the known and the unknowable, between the familiar chemistry of our own biosphere and the alien possibilities that might exist in the hydrogen-wrapped oceans of worlds unlike any in our solar system. The universe has already surprised us with the incredible diversity of planetary atmospheres and the exotic chemistry that operates under conditions we never imagined. K218b may yet hold the greatest surprise of all, the confirmation that life has found ways to flourish in environments that stretch our understanding of what's possible in the cosmic dance between chemistry and biology. The story continues to unfold in laboratories and observatories around the world, where dedicated researchers work to extract every possible insight from observations that push the very limits of our technological capabilities. Each analysis reveals new complexities, each theoretical model suggests new possibilities, and each observation brings us incrementally closer to answering one of humanity's most profound questions. In this patient pursuit of cosmic truth, we find not just scientific advancement, but a reflection of our species' most noble qualities, our insatiable curiosity, our commitment to understanding, and our courage to seek answers, even when those answers might fundamentally change how we see ourselves and our place in the vast, mysterious, and potentially life-filled universe that surrounds us. The methodical approach required to validate these extraordinary findings reflects the painstaking nature of revolutionary science. Every measurement must be cross-referenced, every potential source of error eliminated, every alternative explanation thoroughly explored before researchers dare whisper the possibility that we might be looking at genuine evidence of life beyond Earth. The statistical significance threshold that separates intriguing observation from confirmed discovery has become the focus of an international scientific effort, unlike anything we've witnessed in modern astronomy. The computational challenges alone are staggering. Modern spectroscopic analysis requires algorithms capable of processing wavelength measurements accurate to parts per billion, distinguishing genuine molecular signatures from the countless sources of interference that plague observations across interstellar distances. The data from each transit observation contains millions of individual measurements, each one carrying a fragment of information about K218b's atmospheric composition. Extracting meaningful patterns from this ocean of numbers requires computational techniques that push the boundaries of what's possible with current technology. Machine learning systems specifically designed for astronomical applications are being trained to recognize patterns that human analysts might miss entirely. These artificial intelligence networks learn to identify the subtle combinations of spectral features that distinguish genuine biosignatures from instrumental artifacts or contamination from Earth's own atmosphere. The algorithms must account for everything from minute thermal variations in the telescope structure to the complex physics of how starlight interacts with atmospheric molecules across 124 light-years of space. The precision demanded by this analysis becomes almost incomprehensible when viewed from a human perspective. Imagine trying to identify a single voice in a crowd of millions, where the voice you're seeking speaks in whispers while surrounded by the roar of countless other sounds. That begins to capture the challenge facing researchers as they hunt for the faint molecular signatures that might indicate biological processes operating in K218b's alien atmosphere. Yet beneath these technical challenges lies a more fundamental question that strikes at the heart of how we understand life itself. The molecules potentially detected on K218b exist in concentrations thousands of times greater than anything we observe in Earth's atmosphere. If these signatures truly indicate biological activity, we're looking at life operating on scales that dwarf our terrestrial experience. The implications stretch beyond simple detection into realms that challenge our basic assumptions about how biological systems function. Consider the energy requirements for producing dimethyl sulfide at the concentrations potentially observed on K218b. On Earth, marine phytoplankton create this molecule as a byproduct of their normal metabolic processes, but the total global production remains relatively modest compared to what might be occurring on this distant world. If life is indeed responsible for K218b's atmospheric chemistry, it would have to be operating with an efficiency and scale that makes our planet's biosphere seem almost modest by comparison. The theoretical models being developed to explain these observations are pushing into territory where biology meets planetary science in ways that have never been explored. Researchers are attempting to understand how vast oceanic ecosystems might function under atmospheric pressures dozens of times greater than those at Earth's surface. The physics of gas exchange between organisms and their environment becomes radically different under such conditions, potentially enabling biological processes that would be impossible in our familiar low-pressure atmosphere. The chemical pathways available to hypothetical life in K218b's hydrogen-rich environment represent another frontier in our understanding of biological possibilities. Terrestrial biochemistry operates within the constraints of an oxygen-rich atmosphere where certain chemical reactions are thermodynamically favourable, while others remain forbidden. The hydrogen-dominated chemistry of a Hycean world could enable entirely different metabolic pathways, potentially supporting forms of life that exploit chemical energy sources unavailable to organisms on Earth. Laboratory experiments designed to test these theoretical possibilities are revealing surprising insights about life's adaptability to extreme conditions. Researchers are exposing terrestrial microorganisms to simulated Hycean environments, subjecting them to high-pressure hydrogen atmospheres while monitoring their survival and metabolic activity. The results suggest that the boundary between habitable and uninhabitable conditions might be far more flexible than we previously imagined. Some bacterial species not only survive exposure to hydrogen-rich, high-pressure conditions, but actually show enhanced metabolic activity under certain circumstances. These findings don't prove that life exists on K218b, but they demonstrate that the environmental conditions on Hycean worlds might indeed be compatible with biological processes. The experiments are expanding our understanding of life's fundamental requirements while providing crucial context for interpreting the atmospheric observations. The isotopic signatures hidden within K218b's spectroscopic data offer another potential pathway toward understanding whether the observed chemistry reflects biological or purely physical processes. On Earth, living organisms often preferentially incorporate lighter isotopes of carbon, sulfur, and other elements into their biochemical structures. This isotopic fractionation creates distinctive patterns that can serve as fingerprints of biological activity, even when the organisms themselves remain invisible to direct observation. Detecting isotopic signatures in exoplanet atmospheres requires pushing spectroscopic techniques to their absolute limits. The wavelength differences between isotopic variants of the same molecule are often smaller than the measurement uncertainties inherent in current observations. Future generations of space telescopes are being designed with the specific capability to perform such measurements, but current instruments struggle to achieve the precision needed for definitive isotopic analysis across interstellar distances. The temporal dynamics of K218b's atmospheric chemistry add yet another layer of complexity to the interpretive challenge. The planet's relatively short orbital period means that atmospheric conditions might vary significantly as it moves through different phases of its orbit around the red dwarf host star. These variations could influence chemical production rates, atmospheric mixing patterns, and the stability of potential biosignature molecules in ways that affect our ability to interpret individual transit observations. Long-term monitoring campaigns are being planned to track how K218b's atmospheric composition changes over multiple orbital cycles. Such observations could reveal whether the potential biosignature molecules show the kind of temporal variability that might be expected from biological processes. On Earth, atmospheric concentrations of biologically produced gases often show seasonal patterns, diurnal cycles, and responses to ecological changes that create distinctive temporal signatures. The magnetic environment surrounding K218b remains one of the most significant unknowns in assessing the planet's potential habitability. Red dwarf stars are notorious for their powerful flare activity, which can bombard nearby planets with intense radiation and charged particles. Without adequate magnetic protection, such stellar outbursts could gradually strip away planetary atmospheres, making long-term habitability impossible regardless of other favorable conditions. The generation of magnetic fields in sub-Neptune planets like K218b depends on complex processes occurring deep within their interiors. The exotic forms of matter that might exist under the extreme pressures found in these worlds could have electrical properties very different from anything we encounter on Earth. Some theoretical models suggest that superionic ice, a strange phase of matter where hydrogen ions move freely through a crystalline oxygen lattice, might enable magnetic dynamo processes unlike any seen in our solar system. If K218b does possess a strong magnetic field, the interaction between this protective barrier and the planet's thick hydrogen atmosphere could create unique chemical environments that don't exist anywhere else in our cosmic neighborhood. Charged particles trapped within magnetic field lines could drive atmospheric chemistry through pathways that have never been studied in terrestrial laboratories. Understanding these processes is crucial for distinguishing between biological and purely physical explanations for the observed atmospheric composition. The search for additional worlds similar to K218b has intensified as astronomers recognize the potential significance of Hycean planets for astrobiology. Dozens of sub-Neptune exoplanets orbiting in their stars' habitable zones have been identified as potential targets for atmospheric characterization. Each new world studied adds to our growing database of atmospheric diversity among these mysterious planets, revealing patterns that could help us understand which factors are most important for creating potentially habitable conditions. Some of these Hycean candidates show spectroscopic evidence of water vapor and complex atmospheric chemistry similar to what's observed on K218b. Others appear to have much simpler compositions dominated by hydrogen and helium, with little evidence of the complex chemistry that might indicate surface oceans or biological activity. The differences could reflect varying formation histories, different stellar environments, or simply the natural diversity that emerges from planetary evolution processes operating under different conditions. Comparative studies of multiple Hycean worlds are beginning to reveal correlations between planetary characteristics and atmospheric composition that could guide future biosignature searches. Planets with certain mass ranges, orbital distances, and stellar ages appear more likely to show evidence of complex atmospheric chemistry. These patterns are informing theoretical models of Hycean planet formation and evolution, while helping researchers prioritize observational targets for detailed study. The interdisciplinary collaboration required to understand K218b has created unprecedented partnerships between researchers who rarely interact in traditional academic settings. Atmospheric chemists specializing in Earth's stratosphere are working alongside marine biologists who study deep-sea ecosystems. Planetary scientists are collaborating with biochemists to understand how metabolic processes might operate under alien conditions. Computer scientists are developing specialized algorithms for detecting subtle patterns in astronomical data. This cross-fertilization of expertise is generating insights that no single discipline could achieve independently. The complexity of interpreting K218b's atmospheric observations requires understanding everything from quantum mechanical interactions between photons and molecules to ecological principles governing ecosystem stability. The successful integration of such diverse knowledge represents a new model for addressing complex scientific questions that span multiple fields. The technological spillovers from K218b research are already finding applications far beyond astronomy. The ultra-sensitive spectroscopic techniques developed for detecting trace gases in exoplanet atmospheres are being adapted for environmental monitoring, medical diagnostics, and industrial process control. The data analysis methods pioneered for extracting weak signals from noisy astronomical observations are proving valuable in fields ranging from seismology to financial modeling. Machine learning algorithms trained on astronomical spectra are being modified for applications in materials science, where they help identify the composition of unknown substances based on their optical properties. The statistical techniques developed for assessing the significance of potential biosignature detections are finding uses in medical research, where similar methods help evaluate the effectiveness of new treatments based on limited clinical trial data. The international cooperation fostered by K218b research has created collaborative networks that extend far beyond the immediate scientific questions being addressed. Researchers from dozens of countries are contributing observational data, analytical expertise, and theoretical insights to understanding this distant world. The partnerships established for this research are being leveraged for other major scientific projects requiring global coordination and resource sharing. These collaborations demonstrate how fundamental questions about life and our place in the universe can unite scientists across political and cultural boundaries. The search for life beyond Earth represents a common human endeavour that transcends national interests and ideological differences. The spirit of cooperation evident in K218b research could serve as a model for addressing other global challenges that require sustained international collaboration. The educational impact of this research extends into classrooms and public forums worldwide, where the story of K218b is being used to illustrate how science operates at the frontiers of human knowledge. Students are learning about the iterative process of hypothesis testing, the importance of statistical rigor, and the collaborative nature of modern scientific research. The uncertainty and complexity inherent in the research process provide valuable lessons about how knowledge develops through careful observation and analysis. Science museums and planetariums have developed interactive exhibits that allow visitors to explore the challenges of detecting biosignatures on distant worlds. These programs help the public understand both the technical difficulties involved in such research and the profound implications of potential discoveries. The engagement generated by K218b's story is inspiring a new generation of students to pursue careers in astronomy, astrobiology, and related fields. The economic implications of confirming life on K218b would extend far beyond academic research into areas affecting entire industries and national economies. The space sector would experience unprecedented growth as governments and private organizations invested in telescopes, spacecraft, and technologies needed to study other potentially inhabited worlds. Biotechnology companies would rush to understand how life might operate under conditions radically different from those on Earth, potentially discovering new biochemical pathways with applications in medicine and industry. The confirmation would also drive massive investments in fundamental research across multiple scientific disciplines. Universities would establish new departments focused on astrobiology and comparative planetology. Government agencies would launch major research initiatives aimed at understanding the implications of widespread life in the universe. Private foundations would fund expeditions to study extremophile organisms on Earth as analogues for potential alien life forms. Yet the most profound impact would be on human consciousness itself, forcing our species to confront questions about our place in a universe that harbours multiple forms of life. The philosophical implications would ripple through every aspect of human culture, from religion and ethics to art and literature. We would need to develop new frameworks for understanding our relationship with alien life forms and our responsibilities as cosmic citizens. The ongoing analysis of K218b's atmospheric data continues to reveal new layers of complexity that challenge existing theoretical models. Each refinement of analytical techniques seems to uncover additional molecular species and chemical processes that don't fit neatly into either biological or purely physical categories. The planet's atmosphere is emerging as a far more sophisticated system than initial observations suggested, with chemical interactions that operate according to principles we're only beginning to understand. Recent reanalysis has identified potential signatures of complex organic molecules beyond the controversial DMS detection. Trace amounts of hydrocarbons, nitrogen-bearing compounds, and exotic sulfur species create a chemical inventory that rivals Earth's biosphere in its diversity. Whether these molecules represent the products of biological metabolism or previously unknown abiotic processes remains the central question driving continued research. The three-dimensional structure of K218b's atmosphere represents another frontier in our understanding of this distant world. Current observations provide information averaged across the planet's entire visible disk during transit events, but the actual atmospheric composition likely varies dramatically with altitude, latitude, and local weather conditions. Future observational techniques might be able to map these variations, providing much more detailed pictures of atmospheric dynamics and chemistry. Advanced computer models are being developed to simulate the complex interactions between K218b's thick hydrogen atmosphere and its hypothetical underlying ocean. These simulations must account for atmospheric circulation patterns driven by stellar heating, chemical reactions occurring at different pressure levels, and the transport of molecules between various atmospheric layers. The models are revealing that Hycean atmospheres might be far more dynamic and stratified than previously thought. The magnetic field environment around K218b could play a crucial role in shaping the planet's atmospheric chemistry and long-term habitability. Red dwarf stars are known for producing powerful stellar flares that could strip away planetary atmospheres over geological timescales if not deflected by strong magnetic fields. The persistence of complex atmospheric chemistry on K218b might itself provide evidence for magnetic protection, though direct detection of exoplanet magnetic fields remains beyond current observational capabilities. Theoretical studies suggest that the exotic materials existing under extreme pressure in K218b's interior could generate magnetic fields through processes unlike any operating in our solar system. The interaction between such magnetic fields and the planet's hydrogen-rich atmosphere could create unique chemical environments that drive atmospheric chemistry through pathways never encountered on Earth. Understanding these processes is essential for interpreting observations and distinguishing between biological and purely physical explanations for atmospheric composition. The temporal aspects of K218b's chemistry add another dimension to the interpretive challenge facing researchers. The planet's 33-day orbital period means that atmospheric conditions might vary significantly as the world moves through different phases of its orbit. Seasonal effects, if they exist, could influence chemical production rates and atmospheric stability in ways that affect the interpretation of individual observations. As we stand at this extraordinary crossroads in human history, gazing up at that constellation Leo, where K218b quietly orbits its distant star, we find ourselves balanced between the profound and the possible. Whether this hydrogen-wrapped world harbours the first confirmed life beyond our solar system, or simply represents the most exotic atmospheric chemistry we've ever encountered, K218b has already transformed our understanding of what's possible in the vast cosmic theatre around us. The gentle light carrying those potential biosignatures continues its ancient journey toward our telescopes, and with each passing night, we edge closer to answers that could fundamentally change everything we thought we knew about our place among the stars. Until we meet again on another cosmic journey, keep looking up, keep wondering, and remember that the universe still holds secrets waiting to be discovered.